Welcome to Learn Commerce PU online classes. Don't forget to like our video and subscribe our YouTube channel for all the updates.
Welcome to our second PU Computer Science online classes. Now, after completing some important concept that is about our AND gate, NOT gate, NAND gate, NOR gate and exclusive NOR gate here, and also the circuit diagrams. We know the meaning of the circuit diagrams, the translation of Boolean algebra in the gate form, maybe any type of the gate, AND gate, OR gate, NOT gate, that is called as the traditional gate. So is called as the logic circuits or the circuit diagrams. Okay. Now the next in today's class we are going to complete the very important question from examination point of view. So this question going to start about our NAND, NOR as universal gates. I am telling NAND, spelling is the N-A-N-D, NOR, N-O-R. So NAND, NOR, gate as universal gates. So before going to go to the concept universal gate, some point or some note I want to tell about our other gates. And later words I will start some of the NAND and NOR gate. So we can draw or we can design the circuit diagrams. We know now how to design the circuit diagrams by using Boolean expression. Depend on the Boolean expression question, we are going to design the circuit diagrams by using the traditional symbol of the gates. So we can design the circuit diagrams. The circuit diagrams are AND gate, OR gate, NOT gate. We already drawn as we have done so far. Correct? No? We already completed. In last class only we know how to complete by using the traditional symbol of the gate, how to design the circuit diagrams. But in today's class, I want to tell some other gates are there. Some more popular gates are there. The more popular gates are NAND and NOR gate. So the NAND and NOR gate are more popular gate and very less expensive gates and also very easier to design. Okay. So this is some of the note or the advantage of the NAND and NOR gate. So also we know that some of the traditional gates, the gates are AND gate, OR gate, NOT gate can easily be implemented using NAND and NOR gate here. So we can say that by using now whatever I said now, I just in simple words I want to tell, I just said the basic gates like AND gate, OR gate, NOT gate can easily be implemented using NAND and NOR gate. The meaning is very simple. That means by using the NAND and NOR gate we can also construct the AND or NOT. Clear this point? Just by using the gates like our NAND and NOR gate we can construct the gates, that is AND gate, OR gate, NOR gate very easily. So the NAND and NOR gate are also referred to as the universal gate. So clear this point here. Why it is called as the universal gate here? Because the NAND and NOR gate we can, by using the NAND and NOR gate we can also construct the basic gates like our AND gate, OR gate, NOT gate here. Very easily we can construct. Okay. Now this is about the introduction. Now let's, what is universal gate? It's a very important question about what is universal gate. So the universal gate is a gate using which all the basic gates can be designed. Okay. It is a gate by using such gate, that means the NAND and NOR gate, we can also design the basic gates or using which all the basic gates can be designed here. So this is the definition or the meaning of the universal gate here. So clear this point here. the meaning of the universal gate. Now let's, after completing the universal gate, so clear the meaning of about universal gate. So the universal gate is a gate using which the universal gate, the gates are NAND and NOR gate, using which all the basic gates like AND gate, OR gate, NOT gate we can construct. Okay, so this is called as the universal gate. Now let's next thing about our some of the NAND to NOT logic here. Maybe here some of the NAND to NOT logic is there, NAND to AND logic is there, and NAND to OR logic is there, but this logic is very important. Clear this point here. This logic, the NAND to NOT logic, it's a very important questions in this case here. So we can say that now I am going to complete the operation. The operation is the NOT operation by using method like our NAND. So completely I can say as the NAND to NOT logic. Okay, now this is the symbol. So it is a permanent symbol. We can't say, we can't draw by using any type. Clear this one, such NAND to NOT logic. So X complement X. Okay, so this is symbol about our NOT operation. That means our the NAND gate operation. This is the symbol of the NAND gate. Now we know that here X complement of X is that. Now should get it by using the answer X and complement X. So now I am going to complete this simplification. Not X. So not X, that means I need to get such answer. Not X. X, we know that it is the symbol of the NAND gate. Okay, the symbol of the NAND gate in this case here, and should get it complement of X by using NOT operation. Not X is equal, everything is that we need to convert to the NAND only in this case here. So X, NAND, X. Clear this point here? The X, NAND, X. Later next one, the X and X, X and X. And later next one is the NOT. Clear this point here? I am completing first of all X by using this expression X and X NOT. Okay, the X NOT, and this is the De Morgan's, and to complete this theorems or this simplification we need to use the De Morgan's second law. The De Morgan's second law here, and we know that the De Morgan's second law complement the entire function. Complement the entire function, change plus to the dot and dot to the plus. Is it? Okay. Now later and later next one, complement each of the individual variables. So all those method, the De Morgan's second method we need to use while going to solve our NAND to NOT operation. So X and X NOT, okay, complement the entire function. Second, dot symbol is that, so I am going to change to the plus. Clear this point here? And later complement each of the individual variables separately. I need to make the complementation to the variable. So complement X plus complement X, and when you are going to add, maybe the complement X value is 0, 0 plus 0 value is 0, maybe complement X value is 1, 1 plus 1 the value is 1. Clear? So we can say that this is the answer. So the complement of X. Clear this point about our NAND to NOT logic by using complement of the X. Okay. So this is about the some simplification. Now let's, after completing some simplification, the design rule for NAND to NAND logic. Now maybe any information is there, maybe NOR gate is there, or maybe any type of gate is there, but here just we need to replace into the NAND operation only. Maybe any type of gate, but whatever the gate is that, everything need to replace into the NAND operation only. Okay. So question, design rule for NAND to NAND logic. Okay, here. Now the first rule or step 1. Derive simplified sum of the products expression. Derive simplified sum of the products expression. Second, draw a circuit diagram using AND, OR and NOT gates. We need to draw some of the gates like by using circuit diagrams, using the AND gate, OR gate, NOT gate, and later step 3, just replace AND, OR and NOT gates with the NAND gate. Clear this point? But whatever is there, what's the steps is there? Now I am not going to tell just one word here. I want to tell us the whatever in any type of gate is there, such gate we need to replace into the NAND operations, to the NAND gate here. So now let's the question. Maybe if you are going to tell again and again, maybe you can't understand what about this step and why we need to use this step or what's the meaning of this step. But when you are going to use one example, maybe it will be clear to everyone. So now let's, by using one example, I am going to complete the design rule for NAND to NAND logic. Example, draw the diagram of a digital circuit. Okay. Question, draw the diagram of a digital circuit. Now the question, XYZ is equal YZ plus XZ using NAND gate only. I underline also here. So whatever is that, the Boolean expression is that, but we need to replace, we need to change into, that is using NAND gate only here. So the solution. So in this solution, I already said whatever is that need to replace into the NAND gate. Correct, no? So actually it's a Y and Z. Actually it's a Y and Z. But we need to change to the Y NAND Z. Clear this point here? So Y NAND Z. And actually it's a OR. Is it? It's a OR. But everything going to change to the NAND. Clear this point here? Next one, X and Z. Correct, no here? It is, actually it's a X and Z, but we need to change to the X NAND Z. Clear? So the first step, derive simplified sum of the product expression. This sum of the product expression, that is about our plus sum of the product. Sum of the product. Okay? So this is about our step 1. We need to take this step 1. Plus is the sum of the product. You know about the max term, how we are going to write. So max term, the max term going to write as the A plus B plus C. Correct, no? Here A plus B plus C. So we can say that here in this case A plus B plus C, and later next one A plus D plus C. So in between dot is that. So here we can say that this sum of the product. Clear this point? This sum of the product. So here we can say first of all here this sum of the product. Okay, this sum of the product here. And later this second thing, draw a circuit diagram using AND or NOT gate and just replace AND or NOT gate with the NAND gate. We already replaced whatever is there here. Whatever is there, maybe our AND or NOT gate going to replace into the NAND gate only. Okay. So Y NAND Z plus change to the NAND X NAND Z. Now the diagram. Y and Z, Y and Z, and NOT symbol is there. Clear this point here? Y and Z and NOT symbol is there. Now we completed this one. Okay. Now later next one, again going to connect to the NAND. Later words, let's see. Later words we are going to draw. Now again I am going to take the first front gate, that is X NAND Z. So X and Z NOT. Correct, no? Here NAND means not and here. So X and Z NOT. So and both are going to connect to the our NAND, that is the AND NOT. So AND NOT. So like that we are going to complete. So it's called as the design rule for NAND to NAND logic. So whatever the gate is that, just only going to convert to the gate like a NAND gate. Okay. So Y, NAND Z, NAND X, NAND Z. Everything I converted by using AND to NOT here. So Y and Z NOT, X and Z NOT, and later connecting to the AND NOT. So finally YZ plus ZX. Now the second example for the design rule for NAND to NAND logic. We know that derive the expression by using some of the products here, or maybe anything is that such one going to replace, maybe the AND gate, OR gate, NOT gate, anything is that, everything going to replace to the NAND gate only. Okay. Now this second example, draw the diagram of digital circuit. We are going to draw some of the diagram of the digital circuit. The question, ABC is equal AB plus BC plus CD using NAND to NAND logic only. So clear this point here. Just whatever is that, every going to convert, replace to the NAND to NAND logic. Solution A, B, C. Now whatever is there in question, the same thing we need to write AB plus BC plus CD. Now such expression going to convert or can be write as the A NAND B. Clear this point here. Actually it is a dot is there, in between dot is there, and we are going to read A and B. But we know that we are in the concept of design rule, that is going to convert from NAND to NAND logic. So whatever is that, need to convert to the NAND only. NAND I am telling. Okay. So here I am going to write as the A NAND B. I just completed this one. Actually it's a A and B, but remember it converting to the NAND. So A NAND B, and later plus sign is there, it actually call as the OR, but need to convert to the NAND. Okay. B NAND C, B NAND C, plus is that, convert to the NAND, and C NAND D. So this is the expression we can write. Clear this point? The Boolean expression we can write in this manner here, and later after completing the Boolean expression, I am going to complete the logic circuits. Okay, the logic circuit for by using the Boolean expression. So here A NAND B. So A and B NOT. We know that the NAND full form is the not and. So A and B NOT. Okay. Later everything going to connect by using NAND. So later words we will write. Now just only going to connect to the NAND gate. Later next one I am selecting this one, B and C NOT, and also going to connect to the NAND. Okay here. So this is going to connect, and later next one is the C and D NOT. So going to connect lastly to the AND NOT. Clear this point here? So I think no need to repeat about this one. Here NAND full form not AND. So how we know that? The NAND just going to write by using in this manner. This is called as the AND gate. Now when you are going to write NAND, so we are going to write in this manner. That means A and B not. So A and B not, B and C not, C and D not, everything connecting to the NAND and not. So we can write as the AB plus BC plus CD. Clear this one? Okay. Now we completed NAND to NAND logic, okay, by using two examples here. So like that only we can complete the other example. Just we need to convert the design rule. We need to convert from only to the one gate. The gate name is the NAND to NAND logic here. And later next one, after that our NOT to NOT logic we already completed. In this class only first I completed about the NAND to NOT logic. So now just only like that only the one symbol, the one simplification I want to solve. Now NOT to NOT logic, NOR, I am telling NOR, and this NOT, NOT, NOT to NOT logic. So this is the symbol, okay. So A or NOT, that is called as the complement of A. Now should get the answer, should get the output. So how we can get such output? By using the expression. I want to get such output here. So such output we can get, just we know that first of all not here, or okay, maybe if you are using just by using not X, we don't want A, but because I already completed by using the X here. So X complement of X, so should get it the value complement of X. So not X is equal to X nor X. Clear this point here? The X nor X. So we can write by using De Morgan's second theorem, complement the entire function and change dot to the plus sign and change plus to the dot sign and complement each of the individual variables. So all those rules we need to follow, and I already said in application of De Morgan's theorem, while going to solve the NAND and NOR operation, we can use the De Morgan's second theorem rules, or some of the theorems of the De Morgan's we need to follow while going to solve NAND to NOT logic, NOR to NOT logic here, and also the other gate while going to solve. So the second theorem, actually how we are going to write? X or X not, okay. So X or X not complement the complement here the entire function, complement the entire function, okay. Now maybe plus sign is that, need to change to the dot. So just I completed and complement each of the individual variables separately. I return complement X and complement X. Maybe when you are using the X value as 0, 0 and 0, the value is 0. So finally we can get the answer, that is complement of the X. Clear this point here? So this is about the NOR X here, or such one we can say as the NOR to NOT logic, just to get it, how to get the output by using the De Morgan's second law. We need to use the De Morgan's second law and we can get the value of the NOR to our NOT logic. Okay, now last concept from this chapter we already completed. Whatever the gate is that we replaced just to the NAND, maybe AND gate, OR gate, NOT gate, anything going to replace into the NAND to NAND logic only. We already know how to complete this example. Now let's the last thing about our design rule for NOR to NOR logic. Now we know that here also the same thing. Whatever the expression, Boolean expression is that, everything going to convert into the NOR to NOR logic only. So first one, derive a simplified product of sums. Okay here. So the product of the sums form the expression. So we can say that the first example I already completed. Here the product of the, that is dot, is called as the product of the sum form. So this is our first step. Now let's whatever is that, later words I will tell. Now first I am going to just read the steps of our NOR to NOR logic. So the first one, derive simplified product of sum form the expression. Second, draw circuit diagram using NOT, OR and gates here. And finally replace, that is called as the substitute NOR gate only. Maybe NOT gate is that, OR gate is that, and gate is the finally we need to substitute replace to the NOR gate only. So this is the rule of the NOR to NOR logic. Now first of all I am going to start. Now before going to start, what's the example for the NOR to NOR logic? Example, represent x plus y and y plus z and z plus x in NOR to NOR form. Okay, so this is the question. So we know that step 1, derived simplified product of the sum form. So the product of the sum form, product of the sum plus is there in between. Okay, the product of the sum. So we completed the first step. Okay, now later next one, draw a circuit diagram using NOT, OR and gate here. So before going to draw here, whatever the expression, boolean expression is there in question, I am going to write by using the solution x plus y and y plus z and z plus x. Whatever is there in question, I completed same in the same manner, no any changes. Now we know that concept design, that is the concept replace to NOR logic only. So x plus is the, actually it's a OR, but we need to change to the NOR. So x NOR y dot symbol is there. So NOR y NOR z dot symbol is there. So change to the NOR, and lastly z NOR x. Clear this concept here. So here whatever the dot symbol is there, or maybe the plus symbol is there, so everything going to change it to the NOR only. So like that only I changed here x NOR y NOR y NOR z NOR z NOR x. Now let's how to complete the circuit diagrams. Okay, the circuit diagrams here. So the first one is the x NOR y. So x or y not. Clear this point here. So we know that the NOR full form is the not or. So x or y not, and later going to connect to the NOR. Later words let's see about. First of all we'll complete the front side diagram. So later next one is the y or z. We know that we already changed such or to the NOR. So y or z not. Clear this point here. This is symbol of OR. This symbol of the OR. Now this symbol is called as the NOR. A or B not. But or A or B, just only A plus B. Clear? So this is the difference between OR symbol and the NOR symbol. This is the symbol for OR and this is the symbol for the NOR. A or B not. So now y or z not. Later next one, the last thing, z or x. So z or x not. So everything I completed depend on the expression x and y not. Later y and z not. Later z and x not. Okay, and everything going to connect to our one gate. The name of the gate is the NOR gate only. So just I connected by using the last thing or not. Finally we can say as the xy plus yz plus zx. Clear this point here. So what about the logic gate, and which one is called as the logic gates here, and how to complete the logic circuit by using the gates only, by using the traditional symbol of the gates. And the logic gate, logic circuit means maybe any translation going to transfer, or maybe any boolean algebra going to translate into the logic circuit in the gate form is called as the logic circuits here. So clear everything? Okay, thank you.
Don't forget to like our video and subscribe our YouTube channel for all the updates.